Good morning again. We start our second press conference of the day, which is on thunderstorms and terrestrial gamma ray flashes. I'll remind again everyone that the speakers will give short presentations and then we'll open the floor for questions from those here and those watching us remotely. We can ask questions on Skype by messaging EGU.media or on Twitter using the hashtag AskEGU. Our speakers at this press conference are Oscar van der Velde, who is a researcher at the Technical University of Catalonia in Spain. Joe Dwyer is a professor at the Department of Physics and Space Sciences at the Florida Institute of Technology. And Marco Tavani, who is a professor at the Institute for Space Astrophysics and Planetology in Rome and at the Department of Physics, University of Rome, Tor Vergata. I'll hand over to our speakers now. Thank you.
Okay, thank you for the introduction. So my name is Oscar van der Velde. Good morning. I'm going to present a little bit of information about what is interesting about these phenomena. So what you see in this figure is most of the transient luminous events that have been observed above thunderstorms in the last 20 years. Some of them are very rare, like the blue jet that you see here. But there are also gigantic jets, which is not drawn here, but it reaches all the way to the ionosphere. But there has been relatively little focus on lightning that escapes the cloud tops. And this is the topic that is very interesting now, because we don't know yet how does a gigantic jet form, for example. I press next. Hello. How do I press next? Okay, then I select the slides like this. Yeah, thank you. So here are, on the right side, example of a gigantic jet that was observed in Reunion Island in 2010. And you can see it comes out of the cloud with a lot of streamers. And a similar, but not a bridging the gap event, so an upward lightning event only, was recorded from a thunderstorm near Barcelona last September. So you see the structure is quite similar. The difference in luminosity might be explained just by the cameras. But so the question then is, these events are very rare. So is this just the first step to the gigantic jet event? And can these upward lightning bolts tell something about their initiation? So here's another example. So you see a lightning channel that lies over the top of the cloud and launches an upward leader. But it does not propagate all the way to the ionosphere. But it is good to understand what happens in these cases. Why does it come out of the cloud, under which conditions? And why does it not continue to develop into a gigantic jet? So the key points is the several rare upward lightning bolts have been recorded over the Mediterranean Sea in 5 nights since 2010. The bolts usually reach a couple of kilometers above the cloud. There are no streamers visible at the top of these events. They are produced by relatively low-topped cold air mass thunderstorms in actually all seasons under the jet stream. I found in all cases, plus some cases that are reported in other countries, very strong winds in the upper levels. So this can indicate a screening layer of a charge being not able to form over the cloud, which allows then the upward propagation of lightning through the weaker charge center at the top. So here is just an example that we have recorded with the Ebro lightning mapping array, which is a key ground infrastructure in support of the ESA's Atmosphere Space Interactions Monitor, which is, where is that event? Oop. There's a slide missing. No, it's here. So here's an example. You see here the cloud top. This is altitude and latitude. So we're looking at a slice of this. And you see that one event sticks out well above all the other lightning and also above the radar-determined cloud top. And here is a time altitude evolution of the flash. And it has a certain structure where you can see a low-level leader here, some sources at 5 kilometers, and a leader passing this level upwards. And it seems a little bit like an inverse bolt from the blue, what we call. So that's all about this, except that the topic what we will continue with is terrestrial gamma ray flashes. And these bolts can also be sources of terrestrial gamma ray flashes. And I think since we don't have that much time to explain this, if you have questions, please ask. Thank you.
Okay, so now. Yes. Okay, so moving on to terrestrial gamma ray flashes. I'm Joe Dwyer from Florida Tech. I'm going to be telling you about a new kind of electrical discharge inside thunderstorms, which we call dark lightning. And since these dark lightning discharges can produce a lot of energetic radiation, such as X-rays, gamma rays, and energetic radiation, I'm going to be telling you about the dark side of dark lightning. Okay, let me first summarize where we're going with this. Okay, so there are large bursts of gamma rays that have been observed from space coming from thunderstorms, and we think a plausible mechanism for this is this new kind of electrical discharge called dark lightning. In principle, the doses that individuals inside aircraft could receive if they were in exactly the wrong place at the wrong time when one of these dark lightning flashes went off would be comparable to, say, a full-body CT scan. However, it's probably not likely that this would happen. Pilots already avoid thunderstorms, and so this would be a very rare occurrence. And the good news is that some of the larger doses that had been estimated previously seem to be even more unlikely. Okay, so terrestrial gamma ray flashes were discovered in the 1990s. Spacecraft that were designed to measure X-rays and gamma rays from astrophysical objects started seeing powerful bursts of gamma rays coming up from the Earth's atmosphere. These were very intense gamma ray bursts. They lasted less than 1,000th of a second. Initially, it was thought that these came from the uppermost parts of the atmosphere, well away from where people are, and so it was initially not considered that these might be a radiation hazard. Later on, about 8 years ago, we realized that these terrestrial gamma ray flashes, as seen from space, actually come from deep within the atmosphere, actually from inside of thunderstorms, where commercial aircraft fly. And so then the issue of what happens if an aircraft is inside a thunderstorm when one of these terrestrial gamma ray flashes goes off, that became an important thing to consider. Now, the problem that we had with trying to figure out what the radiation doses were was we really didn't understand how thunderstorms managed to make these terrestrial gamma ray flashes. I mean, if you think of it, the Earth's atmosphere is usually not considered to be a powerful source of gamma rays. Usually you look at things outside the Earth to study gamma rays. So it was actually quite amazing that they can do this, and for a long time we didn't understand how this happened. But recent advances in modeling have shown us that one very plausible mechanism is that large numbers of energetic electrons and the antimatter equivalent, the positron, are created. These create sort of a chain reaction in the thunderstorm, and there's a large spasm of energetic particles, collapses the field, the electric field inside the storm, and produces these bursts of gamma rays and a lot of radiation. So a lightning detector hundreds of kilometers away would detect this discharge in radio waves and say, yes, that's a big lightning flash, a very powerful lightning flash. Well, it turns out that this lightning flash emits almost no light, at least very little visible light. It would be very hard to see. And so hence the name dark lightning. And so this slide shows on the right is a picture of just normal lightning. That makes a hot channel. It's incandescent, it's very bright. We can see it. We're all familiar with that. Computer simulation of what dark lightning might look like if you had very good eyes is on the left. The color is about right. It would be a sort of a bluish purplish glow that would come from the discharge region. That structure, which looks like a bullet shooting down, is about 1 kilometer across and can discharge large parts of the thunderstorm in less than 1,000th of a second. We have done calculations of the radiation doses produced by dark lightning. The initial estimates, based upon the terrestrial gamma ray flashes, put a wide range of doses that were possible. This shows the effective dose, someone inside an aircraft, again, in the wrong place, in the wrong time, inside a thunderstorm. The only thing we didn't know is how wide the discharge region was. That's because we didn't have models initially. Now new modeling work shows that if you were at the tops of the thunderstorms, then you would get doses somewhere around the range of where you say how much radiation you would get just from natural background sources in a year. This would be about the same as 10 chest x-rays. However, if you're deeper inside the thunderstorm, more of the mid-levels, then the radiation doses inside the aircraft could be substantially larger. And this would be, just to give you a comparison, this would be roughly the level of a full-body CT scan. So again, the message is this is something to consider. This is something to look at to estimate the risk factors involved. However, this is not a reason that people should avoid flying. And I always say that, you know, I'm a very overprotective parent, and I would not worry about flying with my kids. So just to put that in perspective, I'm not telling anyone to avoid flying because of this. Okay, so I'll just put up my summary slide and finish there.
So how do we go to
Okay, so
the
maybe
next,
escape.
All right, yes, I'm Marco Tavani, working at the Italian Institute of Astrophysics. And I would like to present briefly what we have been studying about these gamma ray flashes from the Earth. And we do this recently with this satellite, which actually studies the universe, black holes and very distant galaxies. It is a very sophisticated instrument, and we are very happy to study the Earth, not only the universe, but also our Mother Earth. So we are very sensitive also to issues related, of course, to what happens from the ground. So we have been studying these gamma ray flashes from thunderstorms for many years now. We have accumulated a lot of them. This is an example of 3 of them. You see they last really a millisecond or a few milliseconds, very fast. But the important thing is that we can detect quite large energies, gamma ray energies, from space. So imagine that you are in a cloud and that you have to produce some radiation that a satellite at 500 kilometers above the cloud is able to detect. It's not that easy. So this means that you need a lot of particles to do that. Particles need to be accelerated. And so since the discovery in the 90s by a NASA satellite and the NASA group that this radiation comes from clouds, we were very, very surprised that the atmosphere can act as an accelerator, a very efficient accelerator. So we are very worried about, you see the bottom panels there, these what we call a spectrum. We are worried that the largest energies of the spectrum, okay, these are equivalent of tens or even hundreds of million of volts. Okay, so you have potentials which are able to accelerate particles at very large energies. Okay, so we studied the possible effects of this on a special case of airplanes flying near these regions. Of course, it's a very unlikely event, and we stress very strongly, especially when we talk with the media, that this is not going to happen very often, of course. Okay, so you need the very special conditions. But for the sake of the argument of the study, let's imagine that now you are in a situation where you really go deeply into a bad thunderstorm. Okay? So you are, in principle, affected by, of course, a lightning. Airplanes are very well equipped to sustain electromagnetic discharges from lightning. Okay, so this happens very often, actually. If you look at the statistics, the airplanes are usually struck by a lightning once a year on the average. So it's not a very uncommon phenomenon. But these are special kind of lightning, maybe lightning or accelerators. So let's imagine that now you are in a situation where, of course, you need to consider this sort of cylinder, which can be very wide. Professor Dwyer said that it can be very, very large. If it's very, very large, then the radiation is very dilute, and therefore the effect is very small. We are talking about cases where maybe the cylinder is thinner, and therefore there could be some interesting effects. So we studied that, and in addition to particles, electrons, and gamma rays, that we know they exist, when they hit the structure of a plane, they of course penetrate inside. So indeed the dose that Professor Dwyer studied addresses exactly this issue. That's fine. But in addition to that, there is a nuclear reaction in some way that you can have in the structure of the plane. Photons of large energy that we measure with our satellite can also produce neutrons. And that's a different story, because neutrons are pretty nasty in the sense that we have to study very carefully what the neutrons could do to the plane, not only to the people, but especially to the electronic equipment. And that's exactly what we've been doing. So we studied these effects. I don't have time now to tell you all the details, but electronic devices, and people study them, are very sensitive to neutrons. So to make a very long story short, what we find is that in addition to electrons and gamma rays, neutrons in special conditions might play a role in affecting the electronic equipment. So we have to be very careful about that. And I don't have time to explain these two diagrams, but just to show you that, that there is a sort of parameter space, as we call it. So parameters that we don't know very well, which might, of this phenomenon, which might characterize this lightning at the level that if you are with a very intense beam of radiation, this effect can be very important. So to summarize then, usually this doesn't happen, of course, because normal lightning does not produce this effect. But there could be special cases where this might be the case, and therefore we have to be careful. Okay? So, of course, airplanes have a lot of redundancies, fortunately, and they have a lot of systems to avoid problems. Okay? So, depending on the conditions and depending on the type of irradiation, this might be a problem, but usually it might not be a problem. So really, this is definitely something that we have to say up front. But we need for sure actions. And the first thing is that we have to be aware that this phenomenon exists. Professor Dwyer wrote a nice paper on Scientific American that actually was published in August last year. And if you look at that paper, you indeed have a very beautiful explanation of what we know at the moment about the phenomenon, and that we have to be aware of it. Okay. Also, I think we have to do better use of astrophysical data, because now this, there are several satellites which can detect TGFs. Agile is one. The Fermi NASA mission is another one. But there could be others. So we really need to tell the meteorological services and maybe even airlines that a cloud produced a TGF, and we can do that within some tens of minutes. And so to be aware that that particular region is very excited in some way. There are a lot of high potentials. And this is something that seems to be obvious, but we had a lot of problems in doing that so far. So we really need to convince meteorological people and airlines that this is a very good service that we can do for them. And of course, we have to do measurements, both from the ground, from airplanes, and also from satellites. So we need to improve our knowledge of the phenomenon. and possibly also discussing with the airplane people. The technology improves, but definitely we need to be aware of better shielding and better performance of the electronics. And I think that this phenomenon is a very interesting phenomenon. It's an accelerator, natural accelerator in our atmosphere, and can be linked to a lot of meteorological phenomena. We don't know whether they are linked, for example, with extreme weather events or in general with the climate change of our planet. So I think we have to definitely be studying much, much more about this, and agencies have to be aware that this is a very important issue. Thank you.
Thank you very much. We'll now open the floor for questions. Are there any questions from those here in the room or from those watching us remotely? Do you have a question?
Thanks. Jonathan Amos, BBC. Can I just be clear about what causes the production of neutrons? What is the mechanism that produces those neutrons? And also, it's the case, isn't it, that neutrons can be thrown down into the atmosphere during solar storms. So the aviation industry is particularly aware that their avionics might be susceptible, particularly when they're flying over the poles, yes?
Yeah, this is a very good question. Of course, neutrons are naturally produced all the time. They actually even come down to the ground. They are produced by many effects. One of them, in this case, important, is that when you have a gamma ray of a large enough energy, which is about 20, 30 MeV, mega electron volts, hitting on a nucleus, which could be the oxygen or nitrogen of the atmosphere, or the aluminum, or whatever other, structure of the plane, that excite the nuclei, and the nucleus immediately decays into a different nucleus with a gamma ray, with a neutron, and the neutron have a spectrum, which can be calculated, has been calculated by many people, and also we did that. So these neutrons percolate in the environment. So if to make a good example, when you fly on a plane at about 10 kilometers, the amount of neutrons you receive per second is about 300 times more than what you get from the ground. Okay. But then when you have this effect, which is delivered in a very short time, you have many, many orders of magnitude more than the natural background. Okay. So what we are saying also to the aviation people is that this is not the normal background of neutrons that they are well aware of, but this a phenomenon that should be studied much more carefully and taken care of much more carefully.
And Joe, can I be quite clear? The dark lightning is the gamma ray flash. Is that what you're saying?
Yeah, I would think of it as the gamma ray flash is a byproduct of dark lightning. So there's a new kind of electrical discharge inside the thunderstorm. It does many things. One of them is make the gamma ray flash that's seen from space.
Right, but can you just, you skirted over it very quickly, the mechanism of production for the gamma ray flash, is this an annihilation, is it, between the electron and the positron? What's going on?
No. What happens is you have regions inside the thunderstorm with very strong electric fields. These electric fields are strong enough to accelerate electrons to almost the speed of light. Those electrons make gamma rays. The gamma rays produce positrons. The positrons go down to the bottom, make more electrons. You get a feedback loop that goes more and more and more strong. And so eventually there's a very large number of electrons, positrons, and gamma rays produced in sometimes just a few microseconds.
But is there like a trigger when it just suddenly goes like that, or is it just a general build-up? What's the...
There needs to be sort of maybe a finger that pushes over the first domino. And normal lightning could be a trigger mechanism. So you get a small normal lightning flash in some part of the storm, then the rest of the storm responds with this giant pulse of high-energy particles. And it will also collapse the field, producing very large electrical currents. So from somebody in the outside looking at a thunderstorm in radio waves, they would see a very large current that they may interpret as normal lightning, but it's actually not. It's this sort of exotic kind of lightning, which we call dark lightning.
And just finally from me, Fermi's looking out, so and these other satellites are looking out. You're getting the signal from behind you, so I mean, how do you know it's the Earth and, I don't know, not some astrophysical event behind the Earth? Do you know what I mean? I mean, what's...
Yes, this is an example with algae. You see that the algae was pointing out. So you see this red arrow, and we see these events that we interpret as gamma rays coming from, as you see, not from the top or from the bottom. And when we trace them, actually we find that the direction of these two photons, you see this kind of arrow, this red arrow, this tilted red arrow, if you extrapolate them backwards to the Earth, you see that they are actually coming from that particular region in South America, which was studied an hour earlier by meteorological satellites and so on and so forth. So this is really something that you can do imaging, as you see, studying a black hole, but at the same time you also get gamma rays from the ground.
The second reason is that when you get these gamma ray flash seen on spacecraft, you can look at what was happening at the time below, and most of the time there will be a big discharge inside the thunderstorm at precisely that instant. And so we see this over and over and over again.
Thank
Who
you.
cares? I mean, I could say, who cares about black holes at this level, right? So if we can, so this it's something important, I think, for scientists. We have to be more aware of this phenomena. We have to dig out, of course, in our database for these events. This is the problem that we are facing. But I think we have to be more aware, and I think this should be more important also for our community.
Thank you. Oh, there's a question, Scott. Wait.
So, what is black? What does black lightning look like in optical?
Or dark lightning?
This is a question from Twitter.
Okay, so normal lightning, the reason it's so bright is the electrical currents will heat the air up to about 30,000 Kelvin or 50,000 degrees Fahrenheit. That's about 5 times the surface temperature. The sun, when something's that hot, is very bright. It becomes incandescent and emits a lot of light, just like an incandescent light bulb. Dark lightning does not involve any heating of the air. It involves mainly high-energy particles moving up and down through the thunderstorm. The main mechanism for producing light is called fluorescence. And fluorescence is very inefficient. It produces a very feeble light source. And so if you could actually see it, it would be a blue-purplish glow. It would not be a bright channel. The whole air, large regions of the air would just sort of very briefly be purple.
Thank you. Are there any more questions?
Are these phenomena confined to tropical thunderstorms because of the energy level, or can we find them in higher latitudes as well?
Well, in principle, every thunderstorm could do something like this, but it's the ones that happen to be seen from space are the ones that are taller, which tends to be down more in the tropical region. So if you look at where most of them are observed, it's at low geographic latitudes. But we do get a lot of thunderstorms at higher latitudes too, so we really don't know if they make these things or not. Speculation is they would, but we don't know for sure.
There is, I think, a report by Agile satellites up to into the Mediterranean, or there have been some TGFs recorded at least. But this is the maximum what the satellites can actually see, because most are just orbiting over the tropics.
But this is an important issue, and we have to study more. It's not clear. It's like having a blanket on our latitudes. So if you have a satellite studying our latitudes, it would be difficult to see this phenomena, because these TGFs happen presumably within the clouds, and the clouds are pretty deep in the atmosphere. But on the tropics, the top of the clouds is much higher altitude, so the gamma rays can propagate more easily. So the blanket at the tropics is less effective. So it could be that this is a very common phenomenon. That's why we are worried. Otherwise, we would be worried less.
Is there any interest in having a dedicated sensor at all in space? I mean, the next generation of Meteosat has a lightning imager going up, but that's an optical imager, isn't it?
Yeah, that would be very nice. You know, so far, almost all the measurements that have been done about terrestrial gamma ray flashes have been made with instruments like Agile that were designed to do something else, and the gamma rays are coming up through the backside of the spacecraft sometimes. And so these are not ideal measurements. If we were going to start from scratch and design an instrument that would measure these, we would do something very different. And there are some instruments that are coming along that in the near future that are designed specifically for this.
What are those, Joe? Do you know?
What ASIM is one.
Yes, ASIM is a European project on the International Space Mission that should start shortly. I mean, within a few years.
So, sorry, that's going on the space station, is it?
On the space station, yes.
Right.
And but if you are at the geostationary orbit, very far from the ground, it's very difficult to see this radiation because it's very faint at that distance. So we definitely needed to have more instruments, and we are thinking actually of pretty inexpensive instruments that can be put in future meteorological satellites, and so that we can study this phenomenon much better.
And inside planes as well? I mean.
Oh yes, inside planes. Yes, indeed. There is a very beautiful program that I don't know if it's NASA is involved, but definitely it's the NSF maybe or something in the US, yes, which is called ADEL, and maybe Joe is involved about that. And we want to do the same thing also in Europe, so we would like actually to have the same program also, to have a measurement inside a plane.
Yeah, let me say, so Florida Tech's working with University of California at Santa Cruz on an aircraft instrument called ADEL. It's already flown around thunderstorms in Florida a few years ago on an aircraft, and actually did record a terrestrial gamma ray flash from a nearby thunderstorm. This summer, ADEL is going to fly on an unmanned aircraft, the Global Hawk, around hurricanes, and hopefully there will be some thunderstorm activity around the hurricanes, and we can study this as well.
Pinkas Javits, Sustainable Development Media. I'm totally innocent about anything you were talking now, so I'm asking a stupid question. Is there any relationship between this and flares at in the polar region?
Well, I mean, there are radiation. Okay, yeah, the sun can produce energetic particles that, and also energetic particles can come from the galaxy as well. And these particles, the Earth's magnetic field acts like a shield, and the place that the shield is the weakest is around the poles. And so people that fly a lot over the polar regions do need to be concerned about radiation exposure, especially if you do many, many flights, an accumulated dose, if you fly the polar routes especially. So the risk to people in airplanes, similar topic, but the mechanisms that make the high-energy particles in this case are completely different. In fact, it's a brand new way of making high-energy particles. We really didn't know that this could happen in our atmosphere. We knew that you could do this with solar flares and distant parts of the galaxy, but it's really a brand new thing to realize that this can happen deep in our atmosphere in something as ordinary as a thunderstorm.
Thank you. Are there any other questions? Or from the web, or here in the room? No? Okay, so thank you very much to our speakers. Thank you to all of you who attended. The next press conference is in about half an hour and is on climate, water, soils, and human health. Thank you.
Good. Great. So it's good.